Hello everyone, welcome to week 12 live session of NPTEL's Digital Circuit course. I am Om and today we will solve some questions that will help you in your week 12 assignments as well as your exams. So as a part of this course in this week, we will cover uh, some of the remaining portions of the 8085 processor and very few questions on 8086 also. So I highly recommend you watch this week's videos before attempting your assignments as the videos are very clear and are very detailed to help you solve the assignments. Let's start with the first question. Question is, which of the following flag is not present in 8085 microprocessor? A, sign flag, B, zero flag, C, parity flag, and D, direction flag. Please feel free to use your mic anytime if you want to answer or if you want to ask any doubts, or you can use the chat box also. Right, it's D, direction flag. So if you remember, in our flag register in 8085, right, this is the flags register. We have 8 bits. So 8-bit is for sign, 0, this is not used. Auxiliary carry, not used. Parity, not used. And carry. So we have sign, we have 1 bit for sign, 1 for 0, 1 for auxiliary carry, for parity and carry, but we do not have any for direction. sign, zero, and parity are present. So the answer is D. Okay, so let us go to the next question. This question says push and pop instructions are performed by A. Program counter register, B. General purpose register, C. Stack pointer register, D. Link register. Right, it is C. Stack pointer register. So what basically push and pop commands are? So push commands, if you give push RP is the register pair. So whatever is the content of the register pair, it will be pushed onto the stack. So let's say you do push B. So B refers to the BC register pair. So what will happen if a stack is pointing to some address, let's say uh, 0001. Okay, let's not take 001. Let's take 0010. What it will do? It will decrement first, go to 000F, then put the contents of B here, then decrement once more 000E and put the content of C here. So in one push, it decrements 2 times and stores the contents of B and C register pair. The opposite happens in pop. So anyways, we will see more example of this. So push and pop operations are performed by the stack pointer register. I hope this is clear to all. All right, let us see the next question then. Identify the operation performed by the following 8085 instructions. Push B, push D, pop B, pop D. Try to solve this. Take a minute. Okay. Uh, Anybody else wants to take a guess? Okay. So let's see this. So, okay, let us suppose your BC register pair has the values, let's say 1122H, and DE register pair has the values 3344H. right? And this is your stack. Let the stack pointer be pointing at, let's say 4000H. So once you do push B, so it will, what will it will do? It will decrement first and go to, it will decrement and go to 3 F F F. It will decrement by 1. What it will do? It will first store the contents of B here, which is, let's say, which is 1 1 in this case. Then it will decrement again, go to 3 F F E, store the content of C, which is 2 2. So now you have done this command. Next command is push D. Again, it will decrement, store the content of D register here, which is 3 3. Then decrement again and store the content of E register there, which is 4 4. So now your stack is pointing here, which is, this is 3FF. It is pointing at 3FFC now. So this is after push B and push D. Now you start popping. First command is pop B. What will pop B do? Pop B will, when you do pop B, it means you are want to pop the contents of stack into the BC register pair. So what will happen is, if you have B and C register pair, then when you do pop B, the contents of E will go to C, contents of D will go to B. So your BC would contain now 3344. Then you do pop D. So when you do pop D, then in your DE pair, content of C will come in E, content of B will come in D. So your DE register pair will now contain 1122. Now if you see, both of these registers, initially BC had 1122, DE had 3344, but now it is the opposite. So BC and DE have interchanged their values. So your answer would be option C. The contents of the BC register pair are exchanged with the DE register pair. So one thing to take care is, whenever you want, if you do not want the contents to be changed, so always pop B, pop B. It is, the stack should also always follow last in, first out. So D came into the stack at the last, but D will get out the first. If you want to preserve the value of these register pairs. Otherwise, you see, these exchanges will happen if you do not follow the last in first out rule. Is this question clear to all? Okay, I'm assuming it is clear. If not, please feel free to ask. So let us move on to the next question then. Question says, which of the following statements regarding call and return and RET instructions is false? A, an 8085 program may contain multiple return instructions. B, in an 8085 program, first call instruction may appear before the first return instruction. C, in 8085 program, the first return instruction may appear before the first call instruction. D, an 8085 program may contain multiple call instructions. So you have to tell which one is false. Right, it is option C. So what do these call and return statements do? So let's say you have some main program, you reach some level of program, then you want to jump to some other subroutine. So what you will do, you will do a call instruction. Then you what will it will this call instruction will make you do jump to the subroutine and perform whatever it is execute whatever is written in this part of the code. And at the end of subroutine, you always write the return. This return command will make you go back to where you started from. So you can execute the rest of the main program. So always return comes after call. So first call instruction may appear, then return instruction will appear. Option C is incorrect. So your answer is option C. Okay, I hope this is clear to all. Next question. The program status word PSW register pair of 8085 is made up of. So option D is correct. It is accumulator and flag register. So program status word is actually referred to accumulator plus flag, which are the registers that are used by your ALE, sorry, ALU, arithmetic logic unit. Okay, let's see the next one. Which interrupt in the 8085 microprocessor remains unaffected by the state of the interrupt enable, i.e. flip-flop? Okay, so let's see this question. So there are various interrupts in 8085. So what are interrupts? Interrupts is, let's say you are running some program and suddenly interrupt, what will interrupt do? It is like interrupting someone, right? So you are doing something, but there is some interruption from somewhere that asks you to attend to something urgent. That is an interrupt that happens in a program also. So there are various hardware interrupts in 8085. All have different priorities. So basically, when an interrupt happens, whatever the program is doing, it finishes its ongoing instruction and then do and then it performs what the interrupt is asking to do. So, so there are various interrupts in 8085. So I'll just mention them. Interrupts. So there is INTR, there is RST 5.5, RST 6.5, RST 7.5. There is one more. This is trap, which is also known as RST 4.5. Now, interrupts can be either maskable or unmaskable, and they can be vectored or non-vector. So, maskable means you can delay the interrupt. That means some interrupts comes, but you are doing something important in your program. So you can ignore it for some time and just continue doing whatever you are doing. And non-maskable means you cannot ignore it. Similarly, vectored means interrupt has the address. So vectored has a hard, you can say hard-wired address of ISR. So has a hardwired address of the interrupt service routine. That means interrupt service routine will contain what you want to do when the interrupt arrives. So vectored interrupts are those which have this address fixed, that they already know you need to go to this address and then perform something. Non-vectored interrupts, what they have, they do not have a fixed address of the program. You need to provide the address of what you want to do. So among these, INTR is maskable but not vectored. It does not have a fixed address. RST 5.5 is maskable as well as vectored. Is all these RSTs are maskable and vectored. Trap is not maskable. So you can ignore all these interrupts if you want to, but you cannot ignore it. So this is like the most prioritized interrupt. And it is also vectored. It has a fixed address. So interrupt enable flip-flop is a flip-flop that so if interrupt enable, I write is a EI/DI. This is the condition of interrupt enable flip-flop. If EI equals to 1, what means if any interrupt comes, I have to attend to that interrupt. If DI equals to 1, what it means, I do not want to do anything with the interrupt. Even if the interrupt comes, I will ignore it. So this is only possible for the maskable interrupts. So DI equals to 1 is the case where you can mask an interrupt, but it should be maskable. So if it is maskable, then if and DI equals to 1, what will happen is you can just continue working with your code and ignore the interrupt. So the question says which remains unaffected by the state of the interrupt enable flip-flop, which remains unaffected by these EI and DI, and that is the non-maskable interrupt, which is trap. No matter what is the state of this flip-flop, you have to attend to this trap interrupt. It is not maskable. Is this clear to all? All right. Next question. Which of the following is a non-vectored interrupt for 8085 microprocessor? We just saw it, right? It is INTR. You have fixed addresses for all the remaining, but this one you need to provide an address. Okay, next question. Match the following. So please attempt this. Okay, so what is the answer here? It is option B. So we can just match it here. Interrupt is INTR is non-vectored. RST 5.5 is maskable. Trap is non-maskable. RST1 is a software interrupt. So this is the software interrupt. Rest all these 0.5s and trap and INTR are hardware interrupts. So this corresponds to option B. Is this clear to all? Okay. Next question. Okay, so the question says, what is the starting address of the interrupt service routine for RST 7.5? So basically, we just talked about interrupt service routine in a bit, right? Interrupt service routine is just some addresses which tell the interrupt where to go, what to do, right? So, so for any RST, let's say RST n, the address that particular interrupt should refer to is given by n into 8. So what does this mean? RST 7.5 we have. So what it will we will do 7.5 into 8, which is 8 5 is a 40, 0, 4, 56, 60. It points to 60 in base 10. And if we want to convert it to uh, hexadecimal, so 60, it will be, first let's convert it to binary. It will be 0 0 1 1 1 1 0 0. Okay, so yeah, this is 60 in binary. Now to convert into hexadecimal, let's make pairs of 4. This is C, this is 3. So your hexadecimal address is 003CH. So this, whenever RST 7.5 is interrupt occurs, what your program will do, it will go look into the ISR at the address 003CH. So whatever is written there, it will do. So it will go to say 003CH at this address, and whatever is written uh, in this part of the ISR, it will perform. So the only thing you need to remember is n cross 8 is the address. This is, but in base 10 you need to convert it into hexadecimal form. So your answer is option D. Is this clear to everyone? All right. Next is a similar question. Which of the following instruction is equivalent to call 003H? So what does this call statement do? What it will do is, whenever you do in a program, you call 0038H, what it will do, it will go to this 0038H memory location and then start to do whatever is written here. And as you know, in our interrupt signals also, whichever, if any of these interrupts corresponds to, in its ISR corresponds to this address, then it will also do the same thing. So we need to identify what, which of these points to the address 0038H. Okay, so we'll just do what we did in the previous question, just opposite of it, right? So we have the address 0038H. Let's first convert it to the decimal form, but let's go one by one. So first convert it to binary. So it will be 0000. So it's 38H. So 3 will be 0011. This is 3. 8 is 1000, right? This is 38H in binary form. Now what does this correspond to? This is 0, 2, 4, 8, 16, 32. So this is 32 plus 16. This is in base 2. This is 16 plus 8, which is 56. So you have 56 in base 10. Now, if you divide 56 by 8, right, which will give you 7. So this address should correspond to your RST 7, right? We just saw in RSTN, the address is points to is n cross 8. So your answer should be RST 7. Okay, if there are no doubts, let's move on to the next one. Which of the following interrupts is edge sensitive? Okay, so let's see this. So the interrupts that we have INTR, RST 5.5, RST 6.5, RST 7.5, and T trap. Right? These are all the interrupts, hardware interrupts that we have. So let me write here edge sensitive and level sensitive. So among these, interrupt is not edge sensitive, it is level sensitive. RST is not 5.5 is not edge sensitive, it is level sensitive. 6.5 is also level sensitive. 7.5 is edge sensitive. And trap is both edge and level sensitive. So what does this sensitivity mean? So if some signal is, let's say, edge sensitive, so if you just give this high at just the start of the clock, then this interrupt will be registered by your program. But whereas in this case, where which are level sensitive, you have to keep it high until the entire time period. Trap, you have to keep high from start till the end, till the whole level also. So your answer is which of the interrupts is edge sensitive? It is RST 7.5. Okay. So one thing like you can understand this better is, let's say, this is a 8085 chip. These RST 7.5, 6.5, 5.5, these are all connected, are the external pins available for interruption to some other device, right? Let's say some other device is there which can send signals to these pins to interrupt. Now, what makes RST 7.5 as level sensitive is, so let's say these are your lines of the pin, RST 7.5, RST 6.5, RST 5.5. I'll draw just these three. And let's say this goes into your, let me draw it here. These are your pins. With this, let's say it's your 8085. So here, what is there in 7.5? There is a flip-flop attached. In there, they directly go to the connect to the 8085. So this flip-flop must be edge triggered flip-flop. So as soon as you give it high, this edge triggered flip-flop turns to 1 or 0 according to whatever you have done. So it remains 1 or 0 for the entire time. Rest of these you need to keep giving it high or low, whatever for the 8085 clock cycle. So since this flip-flop is there, this makes the RST 7.5 as edge triggered. So this flip-flop is actually internally connected in the 8085. Okay, hope this makes sense. So let's see the next one. Now you can answer this, right? Which of the following interrupt is both level and edge sensitive? Right, this trap. We just saw that. Okay, next one. Which of the which of the following statements is true for the program given below? So you have some commands here. So first command is, this is enable interrupt, which means when you have written this EI in your program code, now for the rest of your code, if any interrupt comes, you will acknowledge that interrupt. It will not be masked. Then MVI A29H, you are sending some 29H data to the accumulator. Then SIM is a new command that we have not seen yet, right? So what is SIM? It is set interrupt mode mask. So 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 we just talked about masking, right? Masking was delaying the interrupt. So to delay the interrupt, you can do a few things, right? First is use di equals to 1. So if di equal to 1, so whatever interrupt comes, your program will ignore it. Another thing is some maskable, uh, you can say, bits. So all RST 7.5, 6.5, 5.5, they have an additional set of maskable bits. By setting them to 1 or 0, we can mask or unmask them. So Just now I had drawn this, right? I'll redraw this in a better way. So let's say this is okay. So this is your flip-flop that is on in your RST 7.5. Then you have your RST 6.5 and you have your RST 5.5. Now, additionally, you have uh, M 7.5, then M 6.5, M 5.5. Now, these are going in somewhere, right? In your 8085. Actually, this circuitry is also inside 8085 only, just for representation. I am drawing to show which interrupt will be enabled. So, what happens here is these are ended like this. Okay, so let's say you give some interrupt signal. Let's say you give one signal at this pin of RST 6.5. You give one also at RST 5.5. But let's say here it is 0, here it is 1. So where it is 0, what this you have a 1 here. Then you see there is a bubble here, right? So 0, 0, it will make 1 and your output will be 1. So now 8085 has received that RST 6.5 interrupt is there. In 5.5, I've written 1 here. That mask enable is this mask is 1. So that means this RST 5.5 is masked. Now you can ignore this. And how is that? Is it going to happen? So if the 1 is here, 0 will be here, and AND of 1 and 0 will be 0. That means this interrupt is not received by 8085. So by setting 1 in these masked bits, we can ignore that interrupt. Whereas if it is 0, that interrupt will be acknowledged. So these are the masked bits. Now, what is happening here? Let's come back to this part. We have understood we have something new that is known as the masked bits. And we have a flip-flop also that we have seen. Now, okay, now let's talk about what happens with SMI. Sorry, SIM instruction. So what instructions does is it reads your okay, let me say it changes the individual masks of RST pins, whatever we saw, right? M 7.5, 6.5, 5.5, based on accumulator, right? So what does this mean? Let's say in your accumulator, right? So we have 8 bits. This first bit corresponds to the mask of 5.5, mask of 6.5, mask of 7.5. This is mask enable. This is for a flip-flop of 7.5, resetting that. This is not used. This is HDE and SO HDO. Okay. So let's see one by one. So in all these three, these first three, if it is 0, that means it is unmasked or that interrupt is available. If it is 1, that means it is masked. Interrupt is masked. Means interrupt can be ignored. MSE should be 1 to have any effect of these masked pins. If MSE is 0, then ignore M 5.5, 6.5, 7.5. Just ignore whatever the bits are here. So this should be 1 to actually reflect any change due to these bits. Then we have R 7.5. This is just this corresponds to reset RST 7.5 flip-flop. We had a flip-flop here, right? We discussed this. So it just sets or resets this flip-flop. This does nothing. SDE, so these are not of our concern right now, but I'll just tell. SDE is just it is serial data enable, and this is serial data out. So if serial data enable is 1, then whatever bit is stored here, either 0 or 1, it will go to some output device. Okay, so now we have seen what this SIM will do. SIM will change the values at these masks based on the contents of our accumulator. Now coming back to our program, we have EI, then we have MVI A, 29H, then we have SIM. So EI is interrupt enable. So we have enabled the interrupt enable flag. So any interrupt can come in your code. Then we have MVI A29H. So that means you are storing 29H in your accumulator, right? And what is 29H? If I make the accumulator again, so 29 will be 0010 and 9 is 1001, right? Now, if I go refer to this again, what each of these accumulators pins mean. So this is mask of 5.5, right, with another color, mask 6.5, mask 7.5, mask enable, reset 7.5 flip flop. This does not do anything. This is serial data out. Serial data enable is serial data out. Okay, so here we can see M5.5 is 1. That means this one is this masked. RST 5.5 is masked, which is that means this RST 5.5 is unavailable. These two are 0. That means these are unmasked. That means RST 7.5 and 6.5 are available. MSE1, that is just enabling whatever is the contents of these bits. You have no serial data transfer, you have no serial data output. Okay, so your options are, so what will SIM do? SIM will just send these values to your masks here. Okay. So your options are RST 7.5 interrupt is masked. VC 7.5 interrupt is not masked. It is 0. So first option is incorrect. RST 6.5 interrupt is masked. VC 6.5 is also 0. So second option is also incorrect. Then we see RST 5.5 interrupt is masked. So we see 5.5 here mask value is 1. That means this interrupt is masked and it is not available. You can ignore this interrupt. So this one is correct. Serial data transmission is enabled. No, it is not. We have SDE equals to 0. So this is not enabled. So your answer is option C. So for this SIM, you just have to just see what the content of the accumulator is, and then just relate it with this map. If something is masked, that means it is not available. If these values are 1, that means that interrupt can be masked. If it is 0, that means you cannot, it is not masked. Is this clear? Are there any doubts? Okay, so I hope this is clear. Here a similar question. Which of the following statement is true after the following instructions are executed in the microprocessor? You first sending something in A and then SIM. So I'll make this, so attempt this, I'll make what accumulator bits mean again. This is M5.5, M6.5, M7.5. This is mask enable, reset 7.5 flip flop. This means nothing. This is serial data enable, serial data out. So with this reference of accumulator, attempt this question. So we have MVI A2BH. So 2B will be stored in accumulator. So 2B is 0010 and B is A, B, C, D, E. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15 in hexadecimal. So we have B 11. So 11 will be 1, 0, 1, 1, right? So only this one is unmasked. These two are masked. So the answer is the questions are serial data transmission is enabled. This is false. It is 0. RST 7.5 mask is interrupt is masked. It is false. It is 0. It is unmasked. RST 7.5 interrupt is available. This is true. It is unmasked. It is available. RST 6.5 is available. It is false. It is masked. So our answer is option C. Are there any doubts in this? Okay. Next question. Which of the following statement is true for 8085 microprocessor? So now we are talking about something new, which is RIM, right? We just saw what is SIM. It is set interrupt mask. RIM is just opposite of it. That is read interrupt mask. So let's talk a little bit about it. So RIM is read interrupt mask. When we are talking about SIM, what we were doing, it was set interrupt mask. So what it does is based on accumulator value, it used to set the M5.5, M6.5, M7.5. It enabled or disabled the mask in your interrupts. Whereas what it does is it checks in your, let's say we have seen this, right? So this is, let's say, RST 7.5, then it is M7.5. We have RST 6.5, M6.5, RST 5.5, M5.5. So based on what is the conditions of these, it sets some value in your accumulator. So it reads the conditions in these bits and on these pins and sets the values in the accumulator. So how does it set the values in accumulator? So the first bit is for M5.5, then M6.5, M7.5. It is interrupt enabled. Then it is P5.5, P6.5, P7.5, and serial data enabled. So basically, what it corresponds to, this are directly, if it is 1 or 0, it will set 1 or 0 here, right? These we can see directly. Interrupt enable is we have set interrupt enable in our program as high or low. It will set this. T corresponds to what you have applied at these pins of 5.5, 6.5, and 7.5. Whatever it is 1 or 0, it is corresponds to these. SD is serial data enabled or disabled. It just checks that. So based on whatever signals are already present in your chip, in the 8085 chip, it sets the values inside your accumulator. It reads the values on your chip and then sets those value into accumulator, which is just opposite of SIM. So basically it is used just to check the conditions on your interrupts. So let us read the question again, which is the following is true. RIM instruction is used for checking the status of RST 7.5 interrupt. RIM instruction is used for masking unmasking RST 6.5 interrupt. RIM instruction is used for checking the status of trap interrupt. RIM instruction is used for masking unmasking of trap interrupt. So what would be the answer? Right, it is option A. We are just checking. With RIM, we can just check, we cannot set. Same is used to set. RIM is just for read. So we can check the status of RSS trap. It cannot be masked or unmasked. Trap is non-maskable. So this does not make sense. And we are again not masking or unmasking with RIM. We are just checking. Is this clear to all? Okay. Next, we come to some very basic questions about 8086. So most of these 8086 questions are simple and theoretical. So let's see. So does anyone know answer to this? 8086 is a dash bit processor, right? It is 16-bit processor. Next one, which of the following is not true about the 8086? A, it is a 16-bit processor. B, it has dedicated internal clock generator. C, can address up to 1 megabytes of address space. D, operates in two modes. Right. B is the correct answer. B is the false one. So all of these are just told if you watch the 8086 video. In the first video, just in first 5 minutes, all of this has been talked about. So 8086 is a 16-bit processor. It has a dedicated internal clock. This is false. In 8085, what we used to do, we used to connect a crystal oscillator to the pins. And there was an internal clock which used to generate the clock pulse based on this crystal oscillator. Whereas in 8086, you have to supply the clock itself from the outside. You cannot, it does not have a clock generator that can read something from the crystal oscillator. 8086 can read up to 1 megabytes of address space. So if you know 8086 has 20 address lines. So those 20 address lines would correspond to 2 to the power 20 addresses. And it corresponds to 1 megabyte of memory. Unit addresses contain 8 bits. That will 2 to the power 20 will be 1 megabyte. And the last one is 8086 operates in two modes. So it has two modes. One is minimum mode, one is maximum mode. Minimum mode is similar to whatever we have read about 8085, that is just operates as a standalone processor. In maximum mode, it can be connected with multiple processors and they can operate together. Okay, so answer to this one is option B. It does not actually have a internal clock generator. All right, let's see the next one. The operating mode of 8086 after applying active low at MX bar is A minimum mode, B maximum mode, C supervisor mode, D user mode. So we just talked about it has two modes, right? Minimum mode and maximum mode. So there's nothing like supervisor or user mode. We can just eliminate these two for now. So we have this signal pins MN slash MX bar. So MN means minimum, MX bar is maximum. So when this is equal to 1, it operates in minimum mode. When it is equals to 0, it operates in maximum mode. Right? If you see Mn is active high, Mx it is there is a bar over Mx. That means whenever it is 0, it will be in maximum mode. So the answer is B, maximum mode. If you apply active low, that means if you apply 0 at this pin, it will be in maximum mode. Is this clear? Okay. Which of the following pins in 8086 microprocessor are multiplexed with data and address signals? So like in 8085, we have the lower order address bus is multiplexed, right? We have AD7 to AD0. Similarly, in 8085, 8086, we also have multiplex address and data bus, but how many of them are there? Anyone knows this? Right, it's option D. The 16 address buses are multiplexed. It is AD0 to AD15. Okay. Next one, what is the size of instruction queue in 8086 microprocessor? So answer to this is option C, 6. So basically, what is instruction queue? Instruction queue is just it it is supposed to mm, send the next instruction to the uh, execution unit where it stores the opcode of a particular instruction, and the maximum instruction size in 8086 is 8 bytes. Sorry, 6 bytes. The maximum size of an instruction in 8086 is 6 bytes. So the size of the instruction queue is 6 bytes, so that it can store the maximum uh, sized instruction also. Is it clear? It's a theoretical question. I hope you're able to relate. Like in 8085, we have seen some instructions, right? Like add, maybe I can just write, let's say, write it MVI A comma, let's say 20H, right? So this part of instruction in 1 byte, here is 1 byte, right? So this is a 2 byte instruction. Similarly, the maximum instruction size here, it will be in 8086 can be 6 bytes. So for storing this 6 bytes, you need a 6 byte instruction queue. Okay, see the next one. Which of the following instruction is an example of direct addressing mode for 8086 microprocessor? So we have seen this direct addressing in the last class in 8085 also. So yeah, this C, you can relate it from there, right? So direct addressing is when address is given in your instruction, right? So this is direct addressing. What is this? They have mentioned a register. So address is, this is register addressing. So in 8086, we actually have, I think, 11 addressing modes. They are quite more than 8085. This is immediate addressing. Whatever you want to move in BH, you have already given the data itself in your opcode. So the second one is immediate addressing. Last one, what you are doing, whatever is stored in this BX register, you add 08 to it, and then at this address, whatever is there, move to BAX. So this is called based addressing. So direct addressing is option C. Is this clear? Okay. So I think this is the last question for today. Again, addressing mode. So which of the following 8086 instruction utilize the implied addressing mode? Right, it is option A. Implied addressing is where we have no data or address in the instruction. It is obvious what the instruction has to do. It does not require any data or address. So this is implied addressing. Okay. So I think that's it for today. If you have any doubts, you can ask, else we can close the session. All right. So with this, it completes our 12 weeks of live sessions. So this was our last section for our assignments. So there won't be any more sessions after that. I probably will take one more session, a summary session, probably on, I think, 17th of October. I don't remember the exact date or time, but yeah, it could be this. So we may do some revision or some practice problems there. So if you have time, you can attend that. However, it will be announced in your emails like always. So keep a look for that. Thank you, everyone. Dr. Nazia is saying, are there any practice problems for exam? Uh, Let me check. So there is a book, I think it is by the author Morris Mano, some digital circuits book. You can refer to that if you want to practice more. As for this NPTEL exam itself, assignments that are given to you as well as what I have given you, they are more than enough. Or you can also maybe look at GATE uh, digital electronics previous year questions. If you are preparing for some competitive exam, it is better to look at this. But for NPTEL course, for a course exam, your assignments plus live session questions are enough. These will cover everything. But if you're preparing for some competitive exam like GATE, you need to read the book as well as you need to solve the previous year questions. Okay,
Okay, sir. Thank you so much.
thank you. Okay, so let's close this session. We will meet on 17th for the summary session. Okay, thank you everyone for joining. All the best for your exams.